Hey everybody, welcome back to another round of engineering. And yeah, we're going to continue on our discussion. So last time we were talking about linear algebra and introducing these ideas of matrices. And I said, hey, you can use matrices to store information. That's kind of the general idea. And then I said, okay, well, if you're not familiar or if you don't remember matrix multiplication, go ahead and watch that video. If not, skip over to this one. So here we are. Now, we're going to continue on this path of how to use matrices, not only to store information, but also how to solve systems of linear equations more efficiently, faster. And so the main idea for today, when we'll finally get to that answer, but one of the main ideas that we'll have to go through are what I call row operations. And these are nothing special, okay? We give it a name, but it's nothing fancy. Once you understand how matrices store information, then the idea of row operations should hopefully follow naturally from that. Okay? So I don't really have very much to say aside from let's revisit the three equations that we looked at last video. And so I'll write those down first of all. I've got my handy dandy note sheet here. And so we had three equations. Number one being y equals 2x1 plus 3x2 plus 1. Okay. We had a second equation saying y is equal to negative 4x1 plus 2x2. And then finally, we had one that said y is equal to x1 plus x2 minus 2. Okay. So I'm just rewriting the equations that we graphically solved last time. Now we're going to introduce the first thing. The first idea is that I need to put these into, I'm sorry, I'm looking for the term here. I believe it's just called standard form. Okay? So I apologize, I didn't have that down, but I want to take these equations and write them in standard form. What this means is that I want to get all of the variables on one side of the equal sign and any term that does not contain a variable on the other side. Okay. And when I say variable, I mean the independent variables, x1 and x2, but also the dependent variable, y. So any term involving x1, x2, or y, I get on one side of the equation. I'll use the left side. And any term that does not contain a variable, I'm going to move to the right side. Okay? So standard form. So that's the first thing that we're going to do. And to be more specific, I'll go ahead and do it in that order. I'm going to write down the equations with the x1 term being first, the x2 term, and then the y term. So let's go ahead. Let's rearrange these equations. I have something that says negative 2x1 minus 3x2 plus y is equal to 1. Go ahead, write down the other two standard forms. I'll be quiet and write them down. So go ahead, and then you can confirm that you have the same answer at the end. So go. Okay. Pause the video if you're not done. And if you are done, go ahead. Do you have the same three equations in standard form? Say, hopefully, yes. That's just some algebra moving stuff from one side to the other. Now you might ask yourselves, what's the advantage here? Why do I bother putting stuff in standard form? And here is where we're going to use the idea of matrix multiplication. So if you're not familiar, or if you said, oh, I don't need to know that, you do need to know it. Okay, so if you're not familiar, go back and watch the other video, the last video that I posted on that matrix multiplication. But here is where we're going to take advantage of the fact that we can use matrices to store information. I have my three equations written in standard form. And notice that the first column, if you will, if you can think of this as being column 1 right here, column 2 right here, and column 3. Okay. So I am going to rewrite the system of three equations using matrices. So these three equations, I can write it as a single equation, if you will, one equal sign. Okay. But I have to do that using the idea of matrix multiplication. So what am I going to do? I'm going to write down the coefficients for each of my three variables. So you notice I'm just taking the coefficients here. Don't forget the negative signs. Very important. So I will go ahead and write down my coefficients. And notice that I end up with a 3 by 3 matrix of just coefficients. So there's the first part. Now the next part is I am going to multiply my 3 by 3 matrix by this is 3 by 3. I'm going to multiply it by a column vector, a 3 by 1 matrix. Okay. And that column vector will have my variables. In other words, I'll have x1, x2, and y. Now, pause the video for a second. Convince yourself, using the ideas of matrix multiplication, that these three equations, the left side here, is equal to the multiplication of these two matrices together. Good? All right. And of course, I should put the equal sign in, and now I will write another, you'll notice it's a 3 by 1 matrix, right? When I multiply a 3 by 3 by a 3 by 1, I will end up with a 3 by 1. Okay. Rows of the first matrix, columns of the second matrix, that's where I get that from. So I'll write in a 1, a 0, and a 2. So on the surface, it looks like we have actually taken a system of three equations and written it as a single equation. The penalty is that this single equation is comprised of matrices. Okay. So now let me introduce you, that's the standard form, let me introduce you to these row operations. And hopefully you'll see now, if you understand how we're storing the information using matrices, hopefully these row operations will make some intuitive sense. Now, mathematicians, physicists were lazy. Oh, good gravy, we're lazy. Okay. So oftentimes, once you have these equations written, this matrix, which I will call A, the variable matrix, which I call X, and then your resultant matrix, which is usually called B. Okay. Once I have that written down, most of the time mathematicians, physicists, they won't write the variable matrix anymore. What they will do is they will write matrix A, -3, 1, 4, -2, 1, -1, -1, and 1. Okay, so I've repeated the matrix A. You'll see some sort of vertical line, and then the matrix B, 0, 2, something like this. Okay. Again, that's because we're lazy. We don't want to have to write this in here, that matrix in there, the variable matrix. I'm just warning you about that because then the row operations will kind of make a little more sense. Okay? So I'm going to clear this slide. Let me go to the next slide. Give me a second, and I'm going to rewrite this matrix. Okay. So I've just simply rewritten the equations, the three equations, and the matrix representation of those three equations. So now let's go ahead and talk about these row operations. And if you're okay with how we are storing the information in terms of a matrix rather than a system of equations, this will hopefully make intuitive sense to you. So number one, okay, when I'm dealing with row operations, I can swap any two rows. Okay? So in other words, if I want, at any point in time, I can exchange any two rows. Say I don't want the first row. I don't like it for some reason. I don't like -2. I want a positive value in the 1, 1 element. I can simply swap those two rows, being sure that not only do I swap the row in the A matrix, but also the B matrix. So I have to take this entire row and swap it with some other row. That is a legitimate operation. That doesn't change the end result. You say, why is that? Well, if we go back and think about our equation representation of it, all that simply means is that we decided to write one equation before we wrote another one. So intuitively, that should hopefully make some sense that swapping any two rows doesn't change anything. It just changes how which equation we write first. So that's number one. That's the first row operation that you can perform without changing the end results. Second one. Okay. The second one is I can multiply any row by any, and I'll put non-zero, any non-zero constant. I guess it could be a non-constant as well, some variable, but then you don't have a linear equation and, okay. So we're dealing with linear equations here. I can take any row and multiply by any non-zero constant. What does that mean? Well, let's say, for example, I don't want a negative number in the 1, 1 element, and I don't want to perform a row operation. I don't want to have to swap rows. Well, one thing I could do is I could say, well, I'm going to multiply the first row by -1. So instead of a -2, I multiply it by -1. This becomes a positive, that becomes a positive, this becomes a negative, that becomes a negative. I have not changed the end solution. I haven't done anything that will make the end solution any different. Again, going over back to the equation representation, we realize, oh, well, all I've done there is I've taken the left side of equation and multiplied by -1, and I took the right side of the equation and multiplied by -1. So I haven't changed anything. And why stop there? For example, say that you don't want a -2, you would like a +1 in that 1, 1 element. Okay, you notice that, okay, well, all I have to do is multiply the first row by -1/2. If I do it by -1/2, so I go through and I multiply by -1/2. Well, now this first element just becomes +1. And then, of course, the rest of the elements in that row change accordingly. So that's the second row operation. The third one is that I can take any two rows and add them together. And of course, add, subtract as well. Of course, that multiply by a negative number and then add, that's the same thing as subtracting. So I'll just leave it in generic terms. Can add any two rows. So for example, let's say I take the first row and add it to the third row. And I'll rewrite it down here. So we could have something like -2, 3, 1, and 1. We have 4, -2, 1, and 0. And then I'm going to take the first row and add it to the third row. So -2 plus -1 gives me -3. -3 plus -1 gives me -4. And then I have 1 plus 1, which gives me 2. Right? I'm taking each of these elements and adding it to the corresponding element in the third row. And so I also have to do that for the B matrix. 1 plus -2, that gives me -1. Now, although it looks different on the surface, this matrix that I've written is exactly the same as this top matrix. And what I mean by exactly the same is it will give us the exact same values. I haven't changed anything. Well, again, looking at our equation representation, what is this? This is that I took the top equation and I added it to the bottom equation. That doesn't change anything. It changes what it looks like, but it doesn't change what the value of x1, x2, and y are. Okay? Take a minute. Convince yourself that these row operations are okay. Okay? Because this row operation stuff will really help us solving this system of equations. So we're going to use these row operations and sub and solve. I'll put it in quotes, sub and solve, except we're going to do it with matrices. Okay. So let me rewrite, I'm going to rewrite just this matrix representation. Okay, so we're on the next page, and I have rewritten our equation. Okay. Now that we have our row operations, we are going to perform something that is called Gaussian elimination. Gaussian elimination. Okay. What this means is that we are going to perform row operations so that we're going to do a couple of things. Number one is we are going to get a 1 in the 1, 1 element position. In other words, and I'll highlight it here, we would like to perform row operations so that whatever number is in the 1, 1 position is a 1. Okay? We want to make it a 1. After we do that, okay, we are going to perform row operations so that the remainder of column 1 is zeros. In other words, after the 1, 1 position has a 1 in it, we are going to perform additional row operations to get 0 anywhere else in that first column. Follow me so far? Then, the next step, okay, so 3, we are then going to look at the 2, 2 element and make it a 1. Again, by appropriate row operations. So after we do the first one and get that set to 1, we 0 out the column. Then we'll move to the next diagonal element, if you will. We'll turn that into a 1. And guess what the next step is? We'll 0 out the second column. Not clown. And for simplicity, so that it'll go faster, we only need to 0 out the elements below the diagonal. So I'll say 0 out second column below diagonal. And then step 5, rinse, wash, and repeat. We'll go to the 3, 3 element, make it 1, 0 out the rest of the column. Go to the 4, 4 element, get it to be 1, 0 out the rest of the column, and we keep progressing that way. So the thing I'll highlight to you, even though we have a 3 by 3 matrix that we're trying to solve, this process of Gaussian elimination can be extended to any size matrix. Okay, so 3 by 3, a 10 by 10, heaven forbid, 100 by 100. Okay, so this process will always work. The last thing you say, well, wait a minute, Greg, what happens if I don't have a square matrix? That's a legitimate concern. In this course, you will always have a square matrix. Okay. And that's because I will say this. If I have 5 unknowns, how many equations do I need? 5. If I have 10 unknowns, how many equations do I need? 10. Okay. If I have 3 unknowns, how many equations do I need? 3. Okay. In this class, you will always end up with a square matrix. Each column represents an unknown, and each row represents a different equation. And so you will always have the same number of rows as columns. Okay. If you want some other funky situations, go and take linear algebra. Okay. It's a really great subject. So let us now go ahead and perform row operations and do this Gaussian elimination procedure. Okay. So me personally, I'm going to take the first row and divide by -2. Now, it's always good before you actually perform the operation, it's always good to say what you're going to do. So here's how I would do it. I'm going to say multiply first row by -1/2. So it's always good to leave yourself some instructions of what you're actually doing. And so I will rewrite it now. Now, sometimes you can do a couple of different steps in one. You should at least note what those steps are. Okay. I'm going to walk you through one by one, and this is going to take a little while. Okay. In fact, maybe I should say, pause the video for a second, see if you can perform this Gaussian elimination procedure on your own. Okay? Take a minute, pause the video, go at it. Okay. I will now walk you through it. Okay? And hopefully we'll have some sort of agreement at the end. Okay? It doesn't matter what process you use, as long as you perform those row operations correctly, then you should be okay. Okay? So one way to get a 1 in the 1, 1 element would be to multiply the third row by -1, and then swap the first and third row. Row 1 and 3. That would be one way to do it. Okay? That will give you the exact same answer at the end of the day after we go through the whole procedure as what I have proposed, multiplying the first row by -1/2. Okay? I'm going to go ahead and do this one, the one I proposed. So what happens? Well, if I multiply the first row by -1/2, I have 1, 3/2, -1/2, and a -1/2. And I haven't done anything to the other two rows. So I should rewrite this as 4, -2, 1, 0, and -1, -1, 1, and 2. So step 1 in my Gaussian elimination procedure has been taken care of. I now have a value of 1 in the 1, 1 element right here. So the next step, I am going to go ahead and zero out the rest of the first column. So what does that involve? That involves multiplying the first row by 4 and subtracting from second row. So we'll go ahead. Okay, go ahead and do this. And this is why it's usually good try not to mix too many steps together, because you can see where it can get a little bit confusing sometimes. Okay, so multiply the first row by 4 and subtract from the second row. So if I multiply, let me go ahead and rewrite the first row. I'm not going to touch that anymore. Okay. Now the second row, I multiply 1 by 4 and subtract from 4. So I get 0. The next one, I have to multiply 3/2 by 4. It gives me 6. Right? 3/2, so by 4. So 3 times 4 is 12, and then divided by 2. So I have 6. And then I take -2 and subtract 6 from it. So I have -2 minus 6. How about the third one? -1/2 times 4 gives me -2. And so I have 1 minus a -2. Right? 1 times 4, 4 minus 4. Maybe I should write it like this. Let me write it like this instead so we can see explicitly. And then I still have to keep going. I have a -1/2 times 4 gives me -2. And so I have 0 minus a -2. Right? Okay. For the third row, you notice that we don't have to do anything. If I want to make -1 into a 0, I just add 1 to it. So here I'll say first row added to third row. Sorry, I keep erasing things. So I have -1 plus 1. I have -1 plus 3/2. I have 1 plus -1/2. And then I have 2 plus -1/2. Okay? I'll go ahead and write down, I'm not going to do any more row manipulations, but I'll go ahead and write down the simplified matrix. Okay. Next page. Okay, so now I've got my equation, my matrix rewritten. And so now it's time for us to start thinking about how to get a 1 in the 2-2 position. So I'm going to do, let's see, we've got a couple different ways to go at this. To avoid having too many fractions, what I am going to do is multiply row 3 by 2. So let's go ahead and rewrite the matrix now, having multiplied row 3 by 2. So we don't have to touch the first row. We don't have to touch the second row. So I'll just rewrite those, 2. And the third row, there's where the magic happens. If I'm multiplying by 2, this becomes a 1, this becomes a 1, and this becomes a -5. Okay. Yes, indeedy, if you're wondering, I found the mistake in my previous slides. That's why I had those fly-ins. This should be a -5. Okay, I dropped a negative sign at some point. Shameful, I know. Okay, well, at that point, let's see. Now I'm going to swap rows 2 and 3. So I'm going to swap 2 and 3. So I rewrite that again. Row number 1 I haven't touched. So I'll just leave that as is. Row number 2 is now 0, 1, 1, and -5. And row 3 is 0, -8, 3, 3, and 2. And now I have successfully completed the next step of my Gaussian elimination. I have a 1 in the 1, 1 column. I have a 1 in the 2, 2. Excuse me, I shouldn't say column. I should say element. And now what I need to do is zero out the rest of the second column. So you hopefully see where we're going with that. We're going to multiply row 2 by 8 and add to row 3. Okay. So let's go ahead and do that. We don't touch row 1. And I'm going to leave myself a little bit more spacing than usual. Okay. Row 2 we don't have to do anything with. We still have 1, 1, and -5. And it's row 3 that we have to worry about. So 0 times 8 plus 0 gives me 0. I have a -8. And then I have to do 1 times 8 and added. So plus 1 times 8. For the 3, 3 position, I have a 3 plus 1 times 8. Right, I'm multiplying the second row by 8 and adding it to the third row. Last one, I have a 2, And I have to add to that negative 5 times 8. Okay, well, I'll go ahead and simplify. So we have 1 3/2, negative 1/2, negative 1/2. We have 0. We have 1, 1, and a negative 5. And then we have 0. Negative 8 plus 8 gives me 0. So I've now officially zeroed out the second column. And here I have 3 plus 8, which gives me 11. And lastly, 2 plus negative 40. So I have a negative 38 here. Of course, the last step is we have to get a 1 in the 3, 3 position. But hopefully you see how that's fairly straightforward now. We just divide row 3. Okay, so I'll say multiply row 3 by 1 over 11. And so we have our solution. We are almost home free. We have now simplified our 3 equations using row operations to come up with an answer for one of my unknown variables. You say, how is that? Let's look again. Remember, each one of the rows represents a different equation. And now that I have performed the Gaussian elimination, I have the third row, which only contains one variable. If I wanted to take this third row and rewrite it as its own equation, it would be 0 x1 plus 0 x2 plus y, right? I have a coefficient of 1, equals negative 38 over 11. By doing this Gaussian elimination process, we have now identified one of the variables. Okay. But wait, there's more. Now let's go up one row. And I'll go ahead and write this on another page. Okay, there we go. So I've rewritten everything. And I've noticed again that the third row gives you y is equal to 38 over 11. And because we have performed this Gaussian elimination process, we can now go up one row. Let's go and look at the second row and turn that back into an equation. Well, that would be x2 plus y is equal to negative 5. But we now have the value of y, so we can substitute that in, right? We can take the value from the third row and substitute it in. So this is that back substitution piece. So we get something that says x2 is equal to negative 5 plus 38 over 11. Okay, well, 5 over 11, well, it's a common denominator, I guess, is what we need. So we would have negative 55 plus 38. So you'd end up with something like negative 17 over 11 is for x2. So we have our value for y. We now have our value for x2. Let's go ahead and use the first row now. Well, the first row says that x1 plus plus 3 halves x2 minus 1 half y is equal to negative 1 half. And we can go ahead and substitute in the two values for y and x2 to get our value of x1. Right? I'll go ahead and do that. Let's go ahead, and you're probably way ahead of me already. 3 halves minus 17 over 11. I do it this way because I have a tendency, as you have already seen, to drop negative signs inadvertently. So when it comes to actually finding specific values, I tend to do this first. Now I can move everything over to the other side. So we get something that says x1 equals, I'll go ahead and find a common denominator. So I have negative 11 over 22. That's the negative 1 half. Then I have plus 3 times 17. 51 plus 51 over 22. And then I have a negative, which is positive, but then I move it to the other side, so that gives me another negative. So I have 38 over 11. So what is this at the end of the day? We have x1 is equal to negative 49 plus 51. So we get 2 over 22, or x1 is equal to 1/11. Now let's go ahead. We have a sanity check. Remember from the last video, we graphed the three equations and we found a numeric value, right? We just zoomed in on that MATLAB plot until we could read a value off of it. Now we have the actual expressions. Let's go ahead and figure out what is 1 divided by 11. Well, 1 divided by 11 in decimal form is 0.090, and I'll go ahead and say that this is a repeating. So maybe I should do it like this. It looks like it repeats. Okay. x2, well, what is that? Negative 17 divided by 11. So x2 would be equal to negative 1.54, and that again is repeating. And y is equal to, well, what's negative 38 divided by 11? This is negative 3.45 and repeating. Just like what we found graphically. Not a surprise, but we have it in a nice closed form expression now. So that's always a good sanity check. What we did algebraically using row operations gives us the exact same value as when we did it graphically. Now again, I will highlight the importance of the row operations. Is that what happens if we have more than 3 variables? We can't do it graphically, but this idea of using the row operations and the Gaussian elimination process allows us to find the values. Pretty cool, huh? Yeah. So there's one more thing that I'll point out, and then we'll call it the close of the video. And I'll zoom in on this matrix for a second. Right here. Okay. You could, if you want, when you zero out a column, you could zero out entries above the diagonal as well. Okay. That's a fielder's choice. You could zero out the entries above the diagonal as well. And what that will do is that will prevent you from having to do these sub and solve processes at the end. So imagine for a moment if you were to zero out the columns above the diagonal as well, then at the end of the day, you would end up with something like 1, 0, 0, 0, 1, 0, 0, 0, 1. Then you would have something, and you'd have, I'll just call it B1, B2, and B3, whatever those values are. Okay. And then hopefully you'll see that you no longer need to do the sub and solve process. Those values are already there. You're done. Actually, I'm sorry. We know what B1, B2, and B3 should be. I should have put those in. You would have just ended up with 38 over 11, negative 17 over 11, and 1 over 11. So you could perform row operations to zero out above the diagonal. And then at the end of the day, when you have your final answer, you don't have to do any back substitution. Okay. So that's something to keep in mind if you want. I will also point out, secondly, this matrix where you have ones on the diagonal and zeros everywhere else, that is a special kind of matrix called the identity matrix. And usually it's given the variable I. I usually try to put a double hatch in there just to remind myself that it's special. Okay. So the identity matrix, it's a matrix, square matrix, where there are ones on the diagonal and zeros everywhere else. If you have, for completeness, if you have zeros below the diagonal, so if you have some matrix where you have zeros below the diagonal, okay, this is called an upper triangular matrix. And if you have the same thing, but the zeros are above the diagonal, you guessed it, it's called a lower triangular matrix. Okay. So I think that I've taken enough of your time for today. Go ahead and review, but you have a couple of key ideas here. Number one is how to take a system of linear equations and write it in terms of a coefficient matrix, the variable matrix, and the resultant. That's number one, taking your system of equations and translating it into a couple of different matrices, keeping in mind that idea of matrix multiplication. That's the first idea. The second idea is the three row operators. Okay, the three row operations. I can multiply any row by a constant, non-zero. I can swap any two rows. And I can add any two rows together. Those three row operations. That's the second main idea for today. The third main idea is taking the coefficient matrix, applying the row operations in a procedure to solve the system of equations. That is what we call Gaussian elimination. So those three things, okay? Coefficient, forming the matrix, understanding the row operations, understanding Gaussian elimination to solve the system of equations. Okay. I'll leave it there. Our next video, we are going to look at what it means to take the inverse of a matrix. And this is how we can actually solve this system of equations even faster. Okay. It's still related to the row operations, but it will help us avoid having to do that sub and solve process. So stay tuned for that. Thanks for your attention. I'll see you next time.